When a natural disaster occurs, humanitarian organizations rush to the scene to provide aid to those affected. The Humphrey and Prudence Tricklebank Foundation is a humanitarian organization that wishes to provide aid to first responders in these disaster areas. The problem is, the area of interest can be anywhere on Earth. It can be here, or here, or here, or here. Let's assume it's 500 by 500 kilometers, about the size of Utah. In this square, the disaster could be a volcano, a flood, an earthquake, or any imaginable catastrophe. Since images of a disaster area are very beneficial, the Foundation has requested that we provide images in the visible, near-infrared, and thermal infrared spectra. The Foundation has requested that we provide an image of 100% of the area in the visible and near-infrared spectra once a day, and an image of 15% of the area 3 times per day at different times. We also are required to provide one image of 25% of the area of interest once per day in the thermal IR spectrum. Additionally, first responders in the area of interest need to be able to communicate with each other over long distances and beyond line of sight. Using the UHF band, we are required to provide communications repeater access for a minimum of 240 minutes per day with a maximum gap of 120 minutes. So what is the solution to this problem? Our solution is to use communication satellites and imaging satellites in a versatile constellation. Let's go over our imaging constellation. What is our solution to getting all these images of a place that could be anywhere on Earth? Sun-synchronous orbits, meaning they're at a 97.7 degree inclination, and repeat ground tracks. At 567 kilometers altitude, the satellites will pass over the same target area at the same time every day. Since each type of image has different requirements, we needed to be creative with the plane spacing. We'll explain how we actually take the picture later, but we'll go over what the orbits look like for now. For the 100% image in the visible near IR spectrum, we will have 3 planes of satellites spaced in RON. For the 15% image in the visible near IR spectrum, we will have 2 planes of satellites spaced closely in RON. 3 of these sets will give us 3 pictures at different times a day. For the 25% image in the thermal IR spectrum, we will also have 2 planes of satellites spaced closely in RON. Now we'll go over how we put together the image. We'll start with the 100% image in the visible near IR spectrum. We have to take the picture at 5 meter resolution. That's 10 billion pixels, so we can't take it all with one satellite. We divided the target area up into 3 sections. 4 satellites will fly over each section, each using a push-broom scanner to take a strip of the target area. As you can see with the first set of satellites, each satellite will take a fourth of the section. The other 2 groups will gather the rest of the target area in the same way. With this method, we get our 100% picture once per day. Next is the 15% images in the visible near IR spectrum. We only need 2 planes of satellites with 2 satellites per plane for this. Let's call them plane 1 and plane 2. Plane 1 can see from here to here. Plane 2 can see from here to here. Since the 15% can be anywhere in the target area, our satellites can get the image no matter where it is. Say the 15% is here. The 4 satellites can slew over and gather the 15% image. With this method, we get our 15% pictures 3 times a day. Last is the 25% image in the thermal IR spectrum. The planes work very similarly to the 15% picture. Plane 1 can see from here to here, and plane 2 can see from here to here. Although the resolution requirements are lower at 100 meters per pixel, the 25% could be broken up into as many as 5% squares. Since the squares can be anywhere, it's actually better to have the ability to take an image of the entire area. We are successful in getting our 25% picture once per day. Once we have taken all of our pictures, we need to downlink them. To do this, we'll have a dish antennas near the north and south pole for our satellites to send the pictures to. Now that we are done with imaging, let's show you how the communications works. We decided to use orbits in which the inclination is matched to the latitude of the target area. They fly at 625 kilometers altitude. We will need 4 planes with 4 satellites per plane for most latitudes. How do we actually communicate with the target area when we fly over? Because of the shape of our orbits, the satellite can pass over at a multitude of angles and directions. Let's look at one example. The satellite passes over here. It can send a signal between these 2 green lines, but if it looks just straight down, it misses most of the target area. So it will slew over so that the whole target area is covered. With this scheme, we meet our requirement of 240 minutes per day with no more than 120 minutes of gap time. With this plan, we have 24 visible near IR satellites, 4 thermal IR satellites, and 16 communication satellites, which is a total of 44 satellites. Here's the catch. We have to get them all launched and into position in 24 hours. So how do you get 44 satellites to orbit and operational in such a short time? Our solution is to have 4 launch sites spread across the globe: St. Helena, Ascension, Western Australia, and Hawaii. At each of these launch sites, we will have launch vehicles with satellites fully integrated, stored, and ready to go. In less than an hour, the launch vehicles will be erected and ready for liftoff. They will then launch into the designated orbit. Although all the orbits are variable based on the types of satellites and the launch time, each launch vehicle will always drop off 4 satellites into an appropriate elliptical phasing orbit. They will be dropped off one at a time. The satellites will then complete a maneuver into their final circular orbit. The system is then ready to go and save the world. Well, at least 500 by 500 kilometers of it.